Yeah, I'm Shlomo. I'll give the presentation. Ronnie, my colleague and co-author, is also on the call. So Ronnie, feel free to jump in if you have anything to add. I guess the presentation is essentially a merger of two papers. The first paper was indeed published at CHI, and it was called Detecting Personality Traits Using Eye Tracking Data. This is what you have in front of you in black. And then we have a follow-up paper, a follow-up journal paper that's about to appear in ACM transaction on interactive and intelligent systems. And there we also plugged in skilled conductance data. So the title of the longer journal paper is slightly different, but I just thought I will sort of blend the two works in one presentation. So whatever you'll see in front of you in the slides in black, that's the first original CHI paper that was presented at CHI 2019. And then what you'll see in blue, these are the new additions that refer to the journal paper and the skin conductance data. It's mainly black, mainly still the CHI presentation, but you'll see a little parts in blue here and there. You have the list of co-authors in front of you. I should say Ronnie and I were pretty much, both of us had a similar contribution to this work. So we are both of us are the first authors. I was the first author of the conference paper, of the CHI paper. Ronnie is the first author of the journal paper. And then just the last bit, you can see the trophy at the top right. Not only it was published at CHI 2019, it got the Best Paper Award, which we are quite proud of. And I think it's a very nice piece of work. So yeah, happy to present, happy to share, and I'll try to keep the presentation, reasonably short, and then leave some time for discussion. Okay, so let's start. Okay. Can you see the second slide?
Yes.
Okay, fantastic. Okay, so let me start with a motivating story. Imagine you own a store and you want to hire a shopping assistant. Probably have in mind somebody, social, chatty, somebody who can talk to the customers, who can persuade them to buy products. So if I slightly abuse psychological terminology, you are probably looking for an extrovert character, somebody who will be, nice and smiling and talking. People come to you, and how will you know? You get many applications. How would you know who is talkative, who is extrovert? You'll probably interview people. And now when people come and you interview them, if they want this job, they'll probably behave. And if they're smart, they'll probably behave in this way. That they'll be social and chatty and extrovert, because it's reasonably easy to imitate this behavior, to fake this behavior, essentially to behave in this way. So how can you still know if this person is actually an extrovert or just pretending to be an extrovert? Obviously, you'll kind of rely on your observations, on your impressions. If you want to be a little bit more rigorous, and this is what psychologists do these days, you can give some sort of questionnaire, what they call in psychology inventory, when there is a long list of questions saying, okay, in this situation, would you say A or would you say B? In this situation, would you behave like this or would you behave like that? And these are like really established, well-studied psychological tools that can model people, can say if the person is an introvert or an extrovert here. Still, we face the same problem, because if somebody really wants to create a picture to pretend they're extrovert, they can answer the questions in an extrovert way, no matter what they are in reality. So still they can trick the system. They can fake. They can answer the question in an extrovert way. So again, the same question: is there a ground truth? Is there a way to establish objectively if a person is an extrovert or an introvert? So that's how we got to deal with this. We basically tried to come up with an objective and and reliable way to establish those personality traits. And the hypothesis that we had was actually that certain things cannot be imitated, cannot be faked. So psychological responses cannot be faked. For example, if I'm giving this talk and I'm really stressed, you may start seeing me sweating, for example, and I cannot control it. I cannot stop it, right? I may start stuttering. Again, I cannot control it just because I'm stressed and I'm excited. My behavior may change. When we are embarrassed, we start blushing, and we cannot control those things. So this was kind of the question that we started with. Some physiological responses cannot be consciously controlled. And then if we capture those responses, if we mine those responses, do some machine learning with these responses, can we actually say something about personality of the person? So this was the question that we started with. And that's what the whole presentation will be about. Can physiological responses reliably, accurately disclose personality? In this case, it was personality, but you can potentially think of many other applications, of many other use cases to this idea. So we came up with something that we call methodology, or essentially a more abstract way for this personality detection. So what we have here, we have at the bottom left, I hope you can see the mouse, we have at the bottom left this human whom we are trying to model. And we have the data of this human. So imagine we have some ground truths, we have some real data that tells if a person is an introvert or extrovert. I'll get back to this in a few minutes, but imagine that this information is available and it's reliable. Our proposition here is that we will expose this person to external stimuli. We will show to this person something, or we will ask this person to do some little task. This will be the trigger for the responses. We will use some sensing technology that will capture those responses. That will, for example, say blushing, there'll be a camera that will be capturing the cheeks, for example, right? Or I said I might start sweating, there will be some device that will measure micro sweating. That's the skin conductant thing. So we'll deploy some sensing technology that will be capturing those physiological responses. And from there on, it's a reasonably straightforward machine learning exercise. We will process the signal that we are capturing. This is the data processing block sitting here in the middle. And then we'll feed the processed data into a machine learning box that will create predictions that will do, in this case, classification, trying to predict, for example, if a person is an introvert or an extrovert. And then with those predictions, we can go back to the real ground truth data that we have and actually see if the predictions were right or wrong. Okay, so that's where we close the cycle. Again, it's a reasonably sort of, I can't say the methodology is massively innovative. It's probably about putting all these things together, getting them to work, and actually checking how good or how bad these predictions are. So now I'll dive into the specific components of this methodology, the way it was deployed here, and you will still have the methodology in your top right on the slides, and every time one component I'll be talking about, it'll be highlighted in yellow. So first, the traits. I use this word traits without defining actually. So the world of psychology is split into what they call models, psychological models, that in this case, they model personality. And there are lots of ways to model personality. I'm not a psychologist, so I may kind of be slightly oversimplifying the things, but you can think of this as a multidimensional space where different dimensions refer to different personality traits, and that's how they call the trait is essentially one dimension. So for example, one of the most popular models in computing, at least, we use the Big Five, the ocean model, where O stands for openness, C for conscientiousness, E for extroversion, A for agreeableness, and N for neuroticism. You can think of this as a five-dimensional space where every person will have a value. So for example, between 0 and 1, again, just to simplify, we can take the introversion, extroversion dimension, the trait, presented as a continuum between 0 and 1, and every person will be sitting somewhere on this continuum, say 70% extrovert, 30% introvert, 0.7, and then there'll be 4 other dimensions representing the other 4 traits. and altogether a 5-dimensional space, and a person is just a point in this 5-dimensional space. So in this work, we looked at 3 different models. The first one, 3 different psychological models. The first one is called the dark triad, and it's about the bad things that we have. Essentially, it contains of 6 different traits: psychopathy, primary and secondary. Primary is the type of psychopathy that we are born with. And secondary, if you wish, it's the acquired one, the one that we sort of, you know, get during upbringing, adulthood, and so on. So 2 dimensions that, 2 traits that refer to psychopathy, 3 traits that are called Machiavellianism, but they're essentially 3 traits of tactics, views, and morality. And it's about, you know, manipulating others and stuff like that. And the final dimension of this model, called narcissism, you're probably familiar. We're not going into the details of narcissism. The second model is called BISBAS in short, and it stands behavior inhibition and behavior activation. And it contains 4 traits. So behavior inhibition, behavior activation is essentially about things that, you know, that make us do certain things. And behavior inhibition, it's the opposite one, what prevents us from doing something. So for the behavior activation part, we have 3 traits, 3 variables: fun-seeking, drive, and reward responsiveness that can potentially, you know, cause us to do certain things. And behavior inhibition is essentially to what extent somebody may prevent a person from doing something. So, you know, risks, dangers, and so on. And the last model that we dealt with is called Hexaco, or in short, the Big 6. It's an extension of the Big 5 that I've just talked about, with honesty being added as the new 6 trait, 6 dimension. And then neuroticism here is inverse, since it's resilience rather than neuroticism, so kind of stability rather than instability. And openness is slightly rewarded, and it's dubbed as originality, but again, referring to a pretty similar concept. So a 6-dimensional model with 6 traits. So altogether, we have 16 traits across these 3 models. Now, I should only say that all these models are very, very established models in psychology. It just happens to be that in computing, we're exposed much more to the Big 5, but there is a whole world of you know, personality modeling in psychology, and they argue nonstop about, you know, what's the best way to represent certain things. I'll really not get into those discussions, debates. I'll just say we picked these 16 traits across these 3 models. We were guided in this by a psychologist. One of our co-authors on this paper is a psychology researcher, and she guided us which models to use and which traits to model. So that's what we have. And now just the last thing now to sort of to finish the discussion, I talked that we have ground truth information, and we sort of pretend to know the real values of those traits. How do we get them? In psychology, they, as I mentioned, they have those inventories, long questionnaires, and out of those questionnaires, they can calculate. So depending on the answers of the subject to those questions, they can just calculate and say, okay, this person is 70% extrovert, 30% introvert. And again, those inventories are well established, well studied. Psychologists have done a lot of studies about their stability and their reliability. So we just take all this for granted, and you know, the psychology work is there. We just basically take their outcomes, their learnings, and use them here for these 16 traits. Okay, moving on, stimuli. So what were those triggers that were supposed to evoke emotions? In this work, we use, we call them stimuli, and we use 2 types of stimuli, images and videos. Both of them were, again, established stimuli that were validated, were studied in the past, and were shown to actually evoke those emotions. Here is one example that's actually not an image from a data set, but I tried to pick something. You can see this, you know, this cheeky toddler, and you start smiling. You start smiling because he looks cute, he looks nice. So clearly this picture, this image evokes some emotions, positive emotions. So there is a data set called IAPS from a university in the States. The name escapes me now, but it's again validated, established data set that was shown to evoke emotions. What do these images evoke? they evoke, they already come with values of arousal and valence. So arousal, okay, one stands for positive or negative emotions, and the valence stands for the high or low. So, you know, strongly positive emotions, mildly positive emotions, strongly negative emotions, and mildly negative emotions. We have these 4 quadrants, and then in the middle we have neutral images. So you can think of this as a two-dimensional space of valence by arousal, where we have these 4 quadrants plus the neutral images in the middle. So altogether 5 types of images, and we had 10 images from every group, from every block, if you wish. And on top of this, we had the videos, yet another data set called film stim. Again, data set of clips, video clips that were validated, were measured, and were shown to evoke emotions. You have at the bottom the list of emotions that those clips. So we picked 7 clips out of this data set. Again, the Lion King that you have in front of you, it's not a real clip from this data set, but you probably remember this part of the Lion King movie, you know, like really sad part where I forgot the name anyway, this Lion King dies, and it's really sad point. So there are a few other clips. There was a few minutes extracts from Monty Python. Transpotting was there. That was discussed, if I'm not mistaken. You probably know again what part of transpotting I'm talking about. And there were a few other things from, again, famous movies that people measured and people showed in the past that these clips evoke emotions. So altogether 7 emotions, 7 video clips. So 50 images split into 5 sort of groups of images plus 7 videos. These were the stimuli that we used in this work. Sensors. The eye tracking part, we use SMI eye tracking glasses. What you have in front of you now, essentially they capture, these are glasses that have here where you have the red dots at the bottom. They have infrared cameras that are looking from the frame inside into your eyes, and they capture your pupils. So from these 2 cameras, we can measure pupils. They capture pupils and they capture saccades and fixations. Saccades are sharp movements of the eyes, and fixations are the opposite when we fix on something. And then there is, and they can also measure blinks. I should also mention there is another camera sitting in here. Again, I hope you can see the mouse. There is another little camera sitting in here that can capture the gaze. We did not use this information. We captured this information, we have it in the logs, but we have not used this information. So essentially all the data that we used comes from these 2 cameras, and it is associated with 3 things: pupils, there's pupil dilation, saccades and fixations, and blinks. And now the blue part, the skin conductance part, we used another sensor, which is called ProComp Infinity. It's a reasonably sophisticated, reasonably expensive biometric reader that captures a whole lot of things. You can see at the bottom right there, a bunch of a battery of sensors that come with this ProComp Infinity. What we used is this part that's marked with B. This is a skin conductance sensor that goes on 2 fingers. In this case, we put it on a thumb and on a ring finger, and it captures, it measures skin conductivity, skin conductance, and this is affected by microdermal activity. So I talked about sweating at the beginning. Like, it's not like real sweating that you start really sweating, but there is always this micro sweating that what they call micro sweating, microdermal activity that reflects excitement, reflects arousal, if you wish, and this is measured by these 2 electrodes that go on the fingers, and then out of the measurement you can calculate GSR, which stands for galvanic skin response. That's the change in the skin conductivity, in the resistance of the body. We also captured, but not used, blood volume pressure. So this is, I think, the bit that's marked here in D, like a little clip that goes on the index finger, measures the volume of blood going through the finger, and you can associate this with heartbeat and with changes in the heart activity. And then you can measure a few other things. For example, if I'm not mistaken, the part that's marked with E measures the respiration, breathing, and you can measure muscle activity with the part that's marked in C. We didn't use them in this work, so we captured BVP, blood volume pressure. Again, did not use it for the predictions. So these are the two sensors that we used, essentially, and that's the work, the eye tracking sensor from the previous slide, and the skin conductance data from this slide. Now, out of these two signals, we extracted features. Now we were jumping to the machine learning part. We extracted features. I'll try to be reasonably short on the machine learning part. We did not use any deep learning or any fancy stuff. Reasonably straightforward, reasonably old school machine learning. So we did manual feature engineering, feature extraction, and then, as I said, old school classifiers that will come in the next slide. So what were the features that we extracted? Out of the eye data, we extracted 10 features. One feature around blinks, 7 features around saccades and fixations, like average saccade velocity, the sort of the breakdown of time between saccades and fixations, because some portion of the time the eyes are jumping, some portion of the time the eyes are fixated on the image or some part of the image. So altogether 7 different features that we extracted out of the saccade and fixations, and 2 features that were associated with the pupils, horizontal and vertical pupil size. So altogether 10 eye tracking features. Again, I should highlight reasonably straightforward features, reasonably common and widely used features in eye tracking research. And out of the skin conductance data, GSR, we extracted 9 features, mainly related. So it's if you look at the skin conductance data, it's time series data essentially. A signal skin conductance goes up and down, and you have peaks, and you have troughs, and you have various funny things in there. So we extracted signal. We did some simple signal processing and extracted features related to the signal, like the signal, the mean amplitude of the signal, the energy of the signal, phasic signals. We did Hjort transformation, and 3 features were extracted from the Hjort transformation. So altogether 9 features related to the skin conductance signal. So altogether, just to remind you, we had 17 temporal blocks, 10 around the images, because we had five groups of images, and we repeated each group 2 times, essentially 2 circles, and we have 7 video clips that we showed. So altogether we call them blocks, because we could sort of split the temporal line of the data collection into those times where we show a particular stimuli, be it an image, a group of images, or a video. So we call them blocks, temporal blocks. For example, that's a temporal block that's associated with highly positive, with strongly positive images, or a temporal block that's associated with the disgust video clip. So altogether 17 temporal blocks, and for each of these blocks, we extracted the 19 features and eye tracking features and 9 GSR features. So altogether we have 323 features. You will see that we had only 20 odd subjects that we use. So in this case, 320 features, 20 subjects. We need to do some feature selection, and I'll sort of skip the details, the technical details of feature selection, but just to tell you, we needed to do feature selection to understand which features are predictive, which features are important. And machine learning, as I said, before the classifiers, we in principle, we get out of those inventories, we get numbers, say between 0 and 1, 0.7 extrovert, 0.3 introvert. Instead of predicting the exact value on this scale, we sort of simplify the task, and we say, okay, let's split our subjects into 3 buckets: high, medium, and low on every trait, and we discretize them. And then the task was to predict the label, high, medium, or low, which is a classification. If you talk machine learning methodology, it's classification with 3-class classifier, low, medium, and high. We had only 21 subjects, so we had to leave one out evaluation, so essentially training the model on 20 and predicting the last one, and then round robin doing it for other subjects. And we, as I said, we use 7 classifiers, pretty straightforward classifiers, nothing fancy. You can see it in front of you. This is, and the metric that we used in the experiments was classification accuracy. So essentially for every trait, we have 21 subjects. We have 17 traits, so altogether 21 times 17 predictions, 16 traits. So 21 times 16 predictions that we had. How many of those predictions were correct? So if somebody is high on extroversion and our prediction says high, yeah, it's a win. If somebody is high on extroversion, our classifier says low or medium, then it's a fail. And we're just measuring how many of these wins, how many of these ticks we have over the entire prediction. So, and the final bit, data collection, 21 staff and students of a research organization, of CSIRO, normative subjects, no real psychopaths, which should be mentioned, and it's kind of one of the limitations of this work. You know, we didn't have anyone okay, we had people on the extreme ends of those traits, like, you know, say extremely extrovert or extremely introvert, but nobody was you know, diagnosed as such with psychopathy or anything like this. So normative subjects. Fixed lab condition, which is, you know, same timing, same illumination, same temperature. They all used exactly the same computer to collect the data, was exactly the same settings, so try to keep these things as fixed as possible. And the overall data collection was about 55 minutes per subject. That's what you see in front of you. So the yellow bit is essentially putting all the sensors and calibrating them and making sure that they are collecting what we are supposed to collect. The green parts are the inventories, where we ask them to answer questions, and they and we get the ground truth data. Again, as ground truth as it gets, the same caveat that I mentioned at the beginning. Potentially they could fake it, but since this is not a hiring scenario and there is nothing critical here, we believe that they answered the questions correctly. And then the blue parts are actually the bits where we collected data. So the block of images that took 9 minutes, and 2 blocks of videos, videos 1 to 3, and then videos 4, 5, 6, 7, that collectively took 14 minutes. So this is the data collection. All right, and this is the last image that basically showed how we collect data. You can see here one subject with EEG headset that we did not use, as I said, with eye tracking glasses, with 2 electrodes on the thumb and the ring finger. That's the GSR sensor, and there is one more. It's not an electrode. It's actually this clip sitting on the index finger that measures BVP, blood volume pressure. Again, the things that are marked in blue we used in this work. The things that are marked in red we did not use. We have the signals, we collected the data, but we haven't used them here. All right, I'm getting short in time, so get into the results. So four questions that we tackled here. First, we used a suite of classifiers, and we wanted to see overall which one performs the best. So I'll just very briefly say that naive Bayes in the middle got around 86% accuracy. So about 86% of predictions were correct. It's a 3-class classification, so the baseline is 33%, so we like 2.5 times above a random guess. And I should say this was surprisingly good results. Like we didn't imagine we would get to those numbers, but you know, that's the accuracy that we obtained, 85%. Some other classifiers, for example, logistic regression is not bad, is around 80%. SVM is at 75%. Some are not great. So again, if you go in, if you read the paper, you'll find there are some explanations why some classifiers performed and others did not. I'll probably skip this here just for the discussion. Again, it's all in the paper, presented there very clearly and discussed with references, like properly we explain, we give it to explanation why we get those results. And for GSR, we got slightly different results, but similar trends. Naive Bayes was the best performing classifier with the skin conductance data. So the results that you'll see in the next slide, they're all with naive Bayes classifier. We basically leave the rest behind and focus just on naive Bayes. Second question that we asked, okay, we have this overall performance of 85.7% or 86%. That's what you see actually at the bottom line of the table on the right. But yeah, probably certain models are easy to predict and certain are hard to predict. Or it can go even into specific traits. Some traits are easy to predict, some traits are hard to predict. So we've broken down these predictions into average predictions for every trait taken individually, and there we have 21 predictions because we have 21 subjects with 1 hour validation. So overall, we are getting 86%, but again, as you can see on the right, some traits we get over 90%, those that are marked in bold, we are getting over 90% accuracy. Some are not great. For example, the top one, primary psychopathy, only 76%. Overall, if you look at the entire list of the 16 traits that we have here, all of them score 76% or above. 7 traits score over 90%, which is again reasonably good accuracy. You can have bus fun seeking. You can see bus fun seeking hits 95%. So 95% essentially means 20 predictions out of 21 were correct. That's what we're seeing here. And if you aggregate them across the models, that's the mean scores that you have for the models. So for the dark triad, 85% average, 84.9, for BIS-BUS 88%, and for the big 6 for hexaco, again 84.92, so almost 85% accuracy. Here is a very interesting, one of the really interesting findings that I really like about this paper. You know, some of them we hit 95%, some of them were at 76%, and some are, so like, is there any sort of logic here? Why some are good and some are not so good? So in psychology, all those traits are split into 3 sort of very big, very high level worlds. There is one world that deals with emotion, which they call affective traits, things that are related to affect, to emotions. The other world of traits deals with cognition, with thinking, cognitive traits, which is about, you know, about how we reason, how we think. And there is a third world, which is about the behavior, essentially how we behave, how this manifests in our behavior. So these are the 3 worlds: affective traits, behavioral traits, and cognitive traits, ABC. And apparently there is a trend here. It's not as strong, you know, we don't have enough data to calculate significance and stuff like this, but in general, there is a trend that we are getting higher predictions for affective traits, for those traits that are about emotions. And when you think about it, it's actually, it's making perfect sense, because the triggers, the stimuli that we showed were affective stimuli. They were stimuli that were supposed to evoke emotions, and surprise, surprise, they do evoke emotions, and we are able to predict affective traits, those traits that are associated with emotions. We are able to predict them more accurately than the cognitive traits or the behavioral traits. So again, not something that kind of we designed, but it was very nice to see this behavior. So you have a few examples here, like tactics, use, morality, bus, fun seeking, B's. They're all affective, emotional traits, but it's not all of them, because some affective traits we still cannot predict accurately. But overall, we have this sort of, let me call it, weak trend. And it's a very nice observation. I really like this observation, that it's easier to predict affective traits with affective stimuli, other way around. Actually, affective stimuli allow us to predict affective traits more accurately, which basically brings it back to other things. So if we were about to predict something, for example, cognitive, maybe the task was supposed to be to ask people to solve Sudokus rather than to watch the Lion King videos. Right, because we're targeting cognitive things, cognitive traits, rather than affective traits. And for the GSR, for the skin conductance, the blue part, we again the results were slightly weaker, slightly lower. The overall average was 81.8%, down from 85.7%, but still all the predictions were above 71%, and 5 traits were over Question 3, images or videos, what is more predictive? What is a stronger stimuli, if you wish? Unsurprisingly, you see kind of the middle part of the table, you see images and videos compared, and you can see that on average, videos hit 76.2% accuracy, whereas images are slightly lower, 73.8. So it's easier to predict with videos than with images. Again, not massively surprising because, you know, the videos are moving images with sound, multimodality, all those things probably allow to, you know, they evoke stronger responses and it's easier to predict. And then once you combine the two of them together, you hit the best performance. That's the 85.7 that we saw before. In general, videos are slightly more predictive. It's not a rule because for some traits we still see images performing better. Probably we need more data to understand this. And once you combine the two of them, videos plus images, they are better than either of the two. And we observed the same behavior for GSRs. Video were more predictive than images, and videos plus images combined, multimodal signal was stronger than either of the two. And the last thing, which features were predictive. As I said, we extracted 17 features. You can potentially ask this question, okay, which of the features is the strongest predictor? What's the most important feature? In short, there is no clear answer to this question because different types of features. So what you see here in this table is the groups of features. For example, for eye tracking, links, saccades, and pupils. And then the columns stand for the models and different the overall conclusion, like there is no single clear answer to this question. Different features perform for different models. If I were to pick one, there was a very interesting observation again. The single most performing feature was the blinks. The strongest predictor, average across all the predictions. Blink rate was the single most predictive feature. And when we asked the psychologists, and then there was one particular ratio that really one particular combination of a trait and a feature that really stood out was blinks and psychopathy. Like really the weight there was double, something like double the second highest. And we went to psychologist, our coauthor, and we asked like, what's going on here? It looks like an anomaly. And then she looked at us and said, yeah, of course, there was like a 30 years old paper in psychology that showed that psychopaths don't blink. We obviously didn't know that. This observation that we got in this paper was purely data-driven observation. Just the correlation there was just very, very, very strong, stronger than the rest. And it's nice to see those psychological findings confirmed by the data in a totally data-driven way. And we had a few of them in the paper. Again, you can go to the paper and read this discussion. And if you look at GSR, pretty much, yeah, Hjort features were slightly stronger than the rest, but again, it was not a rule. It did vary across the predictions of the traits. Right, and finally, the last bit. So we had, in the original paper, we had the eye tracking data. In the follow-up, we also plugged in the skin conductance data, and the question that's immediate question that you would want to ask, okay, what happens if you use the two signals together, the eye tracking data and the skin conductance data? So very briefly, still getting the best performance with naive-based classifier. The combined signal outperforms eye tracking data and skin conductance data separately. So we had something like 85.7 for the eye tracker and 81 point something for the skin conductance. Once you plug in the two of them and again redo the feature selection, redo the classification, the overall performance is the overall average is about 90%, and actually 11 out of the 16 traits they jump over the 90% mark. So reasonably good, 90% accuracy overall. Reasonably good performance. And again, for the predictive features, we cannot see a clear trend. Different features perform for different traits, probably just asks for a better investigation, more subjects, more features, more stimuli, stuff like this. So, wrapping it up, that was the question that we asked. Can psychological responses reliably disclose personality? The answer was yes, and actually much more accurately than we expected when we started this work, about 90% accuracy overall. Personality prediction using physiological responses is possible. The accuracy is pretty good. The most interesting observation, as far as I'm concerned, is that affective stimuli, they allow to predict affective traits accurately. And the best predictions we are getting when we are using images and videos together, and then the combined signal, eye tracking, and skin conductance. And sort of the last thing that I would like to bring up is to compare analytically to other works. We cannot compare directly because nobody used these data. It's just we collected these data and we use this data, so we can't really compare the numbers against other methods or other things. But there was another stream of work similar to ours, where but I should say they only measured the big five. We measure 60 different traits. They used a whole battery of sensors, including camera and I don't remember exactly, but they used many more sensors than these two. We used only eye tracker and skin conductance sensor. They used reasonably long videos from memory. Just the duration of their videos was about 1.5 hours. Whereas in our case, it was 9 minutes of images and 14 minutes of videos, so much shorter stimuli, kind of, if you were to do it in the lab, the intervention would be much shorter. And finally, and probably most importantly, our accuracy was much better. Their accuracy was about 60–70%. Again, it was a 2-class classification, so it's hard to compare. But even though theirs was 2-class classifier and ours was 3-class classifier, so our task was harder, we still achieved better performance. So kind of analytical comparison that shows that we win on many fronts. Okay, and finally, as I said, 21 subjects is reasonably small sample size. We need to understand many more things. We would really like to use more sensors, or say EEG. We're really keen to study EEG. We had a little paper on EEG, but it's still not we haven't analyzed it thoroughly. We would like to understand the dependencies and the links between the stimuli and the traits. That's this links and psychopathy example that I used before. There are probably many more links hidden in this data. Some of them may be well known to psychologists, some of them may be new, and the new bits are actually the exciting and the interesting bit here. And another advantage is that we used off-the-shelf components. So everything here was off-the-shelf, like starting from the stimuli that were existing in images and videos, trackers and sensors, they were all existing commercial things. Signal processing and machine learning, they were all old school algorithms, so there was nothing new. In principle, you can think of taking any of these boxes and sort of opening it up. Okay, can we tune these naive Bayes to perform better? Yes, probably we can. Can we extract some unique sort of features that will be very informative in this case? Yes, probably we can, but each one of these black boxes, opening each of these black boxes requires like a separate investigation, separate work that we'll skip. And finally, on top of tuning these off-the-shelf components, I'm really interested in applications of these two medical scenarios and various clinical problems. For example, you can think of neurological conditions where essentially the changes occur in the brain, and the changes may manifest in 10 years' time with some observable symptoms, but the changes in the brain occurred 10 years ago, right? So can, for example, EEG capture some of those changes occurring, and can we predict, hey, this person is likely to develop Parkinson in 10 years' time, for example, right? So these sort of scenarios, which at the moment it's science fiction, neither computing nor neurology are at this level of sophistication, and none of them has this ability, but that potentially this methodology is a step in this direction. Obviously requires much more work with clinicians, with neurologists, with a whole bunch of multidisciplinary projects. So I guess I'll skip the slide of health applications. I'll stop here. Yeah, papers, CHI 2019, that was the original paper. TIIS ACM transactions and interactive intelligence system. That's the long paper with the blue parts of this presentation. ACM interactions, that was the trigger for Victor to reach out to us and invite us to speak here. That was a very short summary and then of this work. And then we have another paper at EMBC where we, as I mentioned, we touched upon the EEG data, very briefly, very shallow analysis of EEG stuff. And then obviously all the technical details are in the paper, especially the TAAS paper. This one should appear in print, I would say, in the coming months. That's why, and CHI 2019, that one is already online, so you can find all the details there. And we still have a bit of time, so I'll be happy to take questions or discuss